ICTP campus without necessity. Avoid going downtown just for fun.
So, he has sent us an email?
Huh?
Has he sent an email?
Yes, he sent us an email.
No email.
I was planning on going on some work market.
Oh no.
Is this like previous email? Always I have years students. I'm disappointed.
Ah, yeah.
That one.
Why is the mail on ICTP mail? Sure. Where is the mail? Okay. Where is the mail?
Huh?
Where has he Has he sent on the ICTP mail?
Yeah, he sent us.
On ICTP mail. Just
Yeah, someone actually lose this thing.
Yeah, it's about, I think, how many euros is it? How many euros? How much?
Like,
14, I think.
not that.
reminder.
I don't want to move.
Huh?
I don't want to move.
Your hand is not already.
Have you seen them?
Let me cut it
My
out.
wife is not sure. Have you
My
seen them?
sister.
I'm just seeing the mail about the reminder on the scientific meeting.
You don't get the acid.
Evan?
Huh?
Don't go down far.
Who said?
Professor.
Who?
Professor
This is
Pizarro.
the mail.
The message
Yes.
just now.
Just now.
Oh, it's new to me.
When did he send the mail?
No, it's not. Let's ask.
Don't go downtown.
But you are in necessity.
Yeah, wait. Why?
That's it.
It is.
If you need to talk about what?
Oh. You want to reply that? Can we talk about professor?
When did
Can
you
you see?
When did you send? Is it today?
This. I don't even know how
When
this
was it?
song
Was it today or yesterday?
already.
It was today.
Today.
Muhammad.
Yeah, I'm not checking my.
Uh,
How comes my wife is not
I
sure?
think it's
What's up?
the founder of his son.
Okay.
So, will my presentation be postponed as well?
Because-
The situation worsens.
What presentation?
The awareness joke.
Definitely.
I don't have a
Should
joke.
not be postponed. I want to get rid of it.
You don't want to postpone?
Huh?
Do you want to postpone?
No. I want to get rid of the presentation because I've been stressed for 2 weeks and I don't want to continue with that stress.
Right? You don't want to continue under pressure. What it is, man. This is an app in Vietnam, like to buy things. And then when I come to Italy already, it keeps sending me the discount, and then it's asked me why long time I didn't buy something.
Yes. Jual.
But I think it must be like more smart, like it's
You can turn off the notif. You don't want. If you don't have.
like it's hard. I need to find my phone.
No, it's just you.
It's
You have any more or to block notification.
What is us? Then I am you.
Good.
Where am I?
Everybody's is checking his phone. Is there something on phone? There's a assignment. There's a concert on. Yeah.
Did he send us an email?
Yeah, Professor is listening.
Huh?
But I didn't see the email.
Yeah, I also will see.
What about?
Or ICTP email.
It's an ICTP.
Oh, okay, that's why.
This is the block everything.
Ah, I got my fiscal code.
You got fiscal code?
Yes.
Please don't keep quiet. I did yesterday.
I have no time. I'm sorry.
She didn't get one.
Buongiorno. Si trasmette il codice fiscale richiesto.
You receive?
Cordiali saluti. Grazie.
Where are you? Where are you?
Where?
Where are you? In your room.
Yeah.
Oh,
Okay,
okay.
my
Yeah, that's
sister.
good.
Are you sleeping?
In the space.
Favorite space.
Yeah.
Please, Martha.
Yeah.
Teach me the
Yeah.
constructed vector. If I follow this guy, I won't do
Yeah.
my
I want you to do today also. Because it takes, I don't know how many days.
Yeah, I think I'll get it next month. Because of lockdown, I don't know.
Or three, I don't know. I cannot open them with how it's open. Okay. 2 pages.
You said that you could pay me.
What the password on the
I'll try doing it also. Needs digital signature,
Certificate.
I'm just grateful I didn't run.
You don't have property line, then it
Today is Thursday.
That was
No, you not received the code.
quite late, I think.
Ma,
Yes?
did you receive the code?
Yeah.
I'll display.
And there is
Probably.
another one, but I cannot.
Hey, did you send the message to the bank office to make the bank account?
Well, did
Did
you
you?
receive your
Yes.
visa code too?
Did you buy
Yes.
SIM card?
No.
You
We don't need SIM card.
Yeah, I don't think that we need SIM card.
you need it to open a bank
Bank
account.
Yeah, you need
Bank account?
SIM card.
But SIM card to open bank account?
Yes, you need
Oh,
one.
so this fiscal code took how long?
Huh?
That's all.
I forget. Less than 1 week.
Oh.
5, 6.
S7.
But I think the office will wait for all of us send the thing and then they will do one time. Yeah.
We should do it.
So
I think
no, you should send the email, just send email and then you buy SIM card later. Send the email to the
bank. What's the?
what is that?
Send me the.
Well, we can buy our own visa SIM card right, without notifying visa.
No, I mean notifying the ICTP office.
They should be notified because we CC them.
No, notify them that we already got the physical.
Usually fine.
And then
They should be notified seriously because we CC them. You don't know when we send we CC them. When the agent, the text agent reply, they should try
But they want
notify.
but they want an official email.
Oh, an interface. Oh, wait, I received it Friday.
Message.
Yeah, come to the Sandra.
Just the
Oh, we have
I
to-
received it. Oh, my
No, it's just. You should avoid going out.
Today, I mean from today.
I want to go there.
Just not tomorrow. If it's
You have to go out of
How about I step on you?
But we should wait.
I think we need to tell them. think you should
Oh. This is a good exercise. So I look mature. Yeah? What is your Christopher? I cannot remember. I just took and sort of screenshot this. Yeah. I just did a selfie and then I also don't understand what size the passport size and sent them. Yeah, for this discount.
So now everything we combine the delay between the two lectures and the
Yeah, I am really behind in reading. Yeah. Are you especially for the board auto mechanics? I'm really behind. I think I did not.
I'm sorry, a bit late. Okay, good morning. I'm sorry that I'm late to start this lecture, so I will share the screen. Oops. What? Yeah, the record. I do everything. And now, just a second.
Can we turn off the camera?
What?
Can I turn off?
Yeah, you can do whatever is needed. Okay, just a second. Here we go. All right. So, one sec. So where were we? Here. Non-ideal gas. Okay, so we started talking about the non-ideal gas, and the first thing we said is that for the non-ideal gas, the energy, which has to be extensive, internal energy, is n times a function of the temperature and the density, or if you want, instead of the density, you can write down the specific volume, V over N. All right? All right. So now, we said that dE dV at constant temperature and number of particles is equal to minus P plus T dP dt, constant volume and number of particles. Sorry, don't you have a, what is the name of the lady there? No. Don't you have a mask?
Yes, she's
Please put it on. I'm sorry, it's just mandatory. I mean, I didn't mean to offend you. It would be nice not to have it. For all of us. And I told you that for the ideal gas, you see that this is equal to 0, straightforward. All right? So let me derive this in a different way. which is a bit instructive because it gives us a different way of looking at things. So dE is equal to TdS minus PdV minus mu dN, right? And in particular, ds, it's an exact differential, right? So ds is ds dt, dt plus ds dv dv plus ds dn dn, right? You agree with me? Mm-hmm. So you see that if I substitute this into the previous, so if I take this and put it in the previous formula, what I get is the following. I get that dE is equal to T ds dt at constant volume and number of particles times dt plus minus P plus T ds dv dv minus mu plus T ds dn dn, right? And now you can use the Maxwell relations to rewrite this as follows, as equal to T ds dt at constant volume and number of particles dt plus minus P plus T dP dt at constant volume and number of particles dV minus mu plus T, let's see, ds dn is going to be equal to what?
The mu dt. The mu dt,
yeah. Correct. You see, life is easy.
Sorry.
Yes.
Is it plus or minus?
What?
The inside after mu, like plus or minus the
the mu dt, I think it's plus.
I mean from previous equation.
From the previous equation, it's a minus. I think it's a minus sign. You're right. Okay, check this sign here. I hope it's correct, but check it. Okay? Should be correct. Okay, so from this we see again that dE dV is equal to minus P plus T dP dt, as we said, at constant volume and number of particles, as we said previously, and this is equal to 0 for the ideal gas. Okay? Now the question is, what about a non-ideal gas? Well, in general, the pressure is going to be a function of temperature. So whenever the pressure, you see, whenever the pressure is a function of is a temperature times a function of the density, so it factorizes in this way, then naturally, when you take this derivative and you subtract minus P, you will get 0. Okay? So now, whenever your equation of state is going to will be in this form, this derivative is going to be equal to 0.
Yes.
Okay? You agree with me? So if this, then d dv is equal to 0.
Yeah.
You agree? It is reasonable, right? Another question is, well, perhaps there is a situation where this is not happening. And this is the case of the van der Waals equation of state. Vd, well, let's see if I'm able to write van der Waals equation of state. So I told you at the beginning of this course that the van der Waals equation of state is an equation of state that is supposed to describe a gas that is not ideal. It's actually a gas of interacting particles. And you see that it's essentially a modification of the equation of state for the ideal gas, in which instead of having, so for the ideal gas we have P times V equal to N times R times T, right?
Yes.
So I can rewrite this as P times V, little v, which is the molar volume. Little v is V divided by the number of moles, equal to R times T. And now so the whole idea of the van der Waals equation of state is to take these two things and modify them to take into account interactions, right? So this is the modification. What is the modification due to interaction? Well, modification number one is that you should think of interacting molecules in a sense from the point of view of short-range interactions as billiard balls, okay? So they have a certain so if you have various molecules, you have a certain volume that is sitting around your molecule within which they cannot compenetrate each other, right? You cannot get through, you cannot squeeze two molecules closer than a certain distance. Because, okay, thank you. Because interactions become too strong and whatever. There is a hardcore potential, essentially, that does not allow you to get closer than something.
Yeah.
So how do you take that into account? Well, you say, I don't have at my disposal, if I think about my molecules as point particles, then the volume is the total volume. But since these molecules are not point particles, but are just balls, then every molecule cannot explore the whole volume, can explore the whole volume minus the volume of all the other balls, right? So there is a certain excluded volume per molecule, and this is taken into account here, right? At the same time, what you have is that the pressure is being modified by the so-called long-range part of the interactions. Why? Well, you can imagine, if I have non-interacting particles and I put them here, right? Well, they will do something, but they will stay here. But if you now start turning on some either attraction or repulsion, well, of course, this cloud is going to have some pressure that depends on the interaction, that will try to make it expand or compress. The pressure is going to depend on the interaction between the molecules. You see what I mean? It's intuitive. I mean, I'm not saying anything spectacular. If I have pressure, if I have molecules and they are interacting, if they repel each other, the cloud will try to expand and will exert some pressure on the walls. That is going to be larger than the pressure I had before, and if they will attract the opposite. So there will be a contribution to the pressure, therefore, that is proportional to the, that is dependent on the long-range part of the interaction, and it's going to depend also on the density. And this is what is written up here. Okay? So this is the idea of the van der Waals equation of state. Yes?
So B is the volume?
B is the excluded volume.
I didn't. What is the meaning?
So it's what I told you before. Suppose that you were a point particle. Suppose. Then you could be sitting everywhere in this room. You had at your disposal the whole room, if all the other guys were point particles. But since you are not a point particle, but you have a certain volume, you cannot sit closer than, well, now with COVID, you cannot, okay, well, now you understand, you have an excluded volume that is very large, actually, with COVID. But even larger than your volume. But even without COVID, you cannot get closer to her than, let's say, one chair. Otherwise, you know, you sit on top of each other, and it's impossible because of interactions for molecules. Same story. So actually, the example of COVID is a good example. So now you have a large excluded volume around you, and if you want to account for it, you have to subtract it, right, from the total volume for the equation of state. So that's the logic. All right.
What's the term then? A
over V squared.
V squared.
Yes.
Why you add A over V squared? Because
Why A over V squared? Well, so V squared corresponds to R to the 6, right?
yeah, V squared.
V squared, so volume is a length to the power 3, right? So a volume to the power, to the square corresponds to R to the 6. Now, what is the interaction between the long-range interaction between dipoles in you know, the van der Waals long-range interaction? How does it go with distance? R to the 6. So that's where this V squared comes from. Lennard-Jones potential, whatever. You see? So that's where it comes from. It essentially accounts for the long-range part of the potential between molecules. So that the power 2 comes from the R to the 6.
The A tells us about the potential.
About this component of the potential. So the B is about the short-range part, the A is about this one.
Because I was trying to think about the dimensional conservation of dimensions with pressure on this and the potentials.
Well, okay, so V is that, well, V has dimensions of a volume per mole, right?
Yes.
So this has dimension of 1 over R to the 6. So the pressure is, well, yeah. A is dimensional, is not dimensionless, and B is dimensional, is a volume divided by number of moles. So both constants are not dimensionless constants, okay? All right, so this said, now that we understand the van der Waals equation of state, at least qualitatively, the most complicated calculation that we are going to do in this course is going to be the derivation of this equation of state. Using statistical mechanics is going to be a total mess, you will see. But very nice, very beautiful calculation. A lot of diagrams and the integrals. What?
Diagrams.
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 Yeah, it's called cluster expansion. So we will have to write cluster diagrams. And it's going to be the first time you see something like a Feynman diagram.
The one you drew.
Well, not the same, something simpler than that. Diagrams in theoretical physics are very useful. All right, so let's go back now to our problem. What we want to do now is the following. Well, first of all, if we have a van der Waals equation of state, what about dE dV? Okay, so dV dV is no. Now, you see that the pressure in the van der Waals equation of state is R times T divided by V minus B minus A over V squared. Now, this A minus A over V squared is crucial. If there was no A over V squared, of course, you were right, you would get 0. But now, since we have this, if we take this derivative, we get A over V squared. Okay?
Yeah.
So this, you can see it as the derivative of the energy per mole divided by the volume per mole, if you divide both of them. So, and then you can ask yourself, okay, if this is the result, so the derivative is not equal to 0 in the van der Waals equation of state. Now, if this is the result, what about the energy if I integrate this equation? Well, the energy per mole is going to be equal to minus A over V plus omega T. That's a certain function of temperature, right? Well, if I know the energy as a function of temperature and volume, what is the first thing that comes to your mind? What can I calculate?
Energy as a function of
temperature and volume. What can I calculate?
the specific capacity.
The specific heat.
Yeah.
Heat capacity or specific heat, right? I can compute the specific heat. And in particular, what I know is that if I have an ideal gas, the difference between the specific heat at constant pressure minus the specific heat at constant volume is equal to R, right? R, the gas constant. So I could ask myself, since I'm starting to think as a researcher, I could ask myself, aha, now I have a gas that is not ideal. Let me try to see what is the difference between constant pressure, specific heat, and constant volume, and see how it changes as compared to the ideal gas, right? How it depends on these two constants, A and B. So this is how you think as a researcher. You try to compare different situations. A situation in which you know everything, the ideal gas, and a situation about which you don't know anything, the van der Waals in this case. All right, so now CV. CV is equal to d epsilon dt at constant volume, and therefore is omega prime of t. Omega prime means derivative of omega. Well, let's write it explicitly. Derivative of omega with respect to t. Now Cp. Cp is d epsilon dt at constant pressure plus P dV dt at constant pressure. Right?
What is omega?
Sorry?
What is omega?
What is?
Omega.
Omega. This.
Yeah, because I didn't touch.
Now, where does this formula come from? Well, you remember that is essentially what we obtained with the dq, the formulas that we wrote down at the beginning when we did those calculations for delta q, for the for the whatever, for the constant pressure situation. And now if we take this derivative, what we get d omega dt minus, well, p dv dt. So this is d omega dt minus d dt a over v. Why? Because epsilon is equal to minus a over v plus omega t. So here I take a derivative with respect to t on both sides, plus p dv dt. Or in other words, if I combine everything together, I get d omega dt plus p plus a over v squared dv dt at constant pressure. And now I have to calculate this dv dt at constant pressure. How do I do that? Well, I do it in the following way. So let me do it here. So I remember that there is an equation of state, P plus A over V squared, V minus B equal to R times T. Now, if I take the differential of this equation on both sides, so what I get R dt plus P minus A over V squared plus 2ab over b cubed dv plus v minus b dp, right? Well, just take the derivatives, it's not a big deal.
Professor.
What?
Where I cannot get the omega dt minus d dt a over v plus b dt.
Which one do you don't get? The omega dt minus?
d dt, from the second term. d dt a over v.
Ah, well, that comes from this, right? Since epsilon is minus a over v plus omega t, right? So, and Cp is d epsilon dt plus p dv dt. Well, I take d epsilon dt, I have d omega dt minus d dt a over v, right?
I get it. Thanks.
You got it? All right, so now from this you get that dv dt, constant pressure, is equal to R divided by P minus A over V squared plus 2AB over V cubed. And therefore, if I substitute now this here, so let me put a, you substitute here, finally you get that your Cp is equal to d omega dt plus R squared T V cubed divided by R T V cubed minus 2A V minus B squared. And now you see something interesting. If I set A equal to 0, you see that since Cv was equal to d omega dt, if I set A equal to 0, you see that the difference of these two guys is just what it is, right?
Yeah.
Both are very
Could be R.
Well, the difference between this and that is R,
Yeah.
which is what you get for the ideal gas, right?
Yes.
So everything is working.
If we set A and B equals 0.
Well, so from here you see that what you have to set really equal to 0 is A. If A is equal to 0, then, well, you get R sitting up there. Well, then if you want to set also B equal to 0, then it's even better. But
I'm thinking that the different approach, the assumptions we started to model the van der Waals interaction is based on us thinking first about the effect of volume and also the effect of the interactions.
Yes.
So saying, okay, maybe it would be good to set both of them 0 and we go back to we keep one, then we have one idea of no interaction, but then the volume
but in a sense,
which is also not ideal gas because we are saying that in terms of volume, the systems in a way can have I don't know.
look, the interaction beyond the short range, I mean, it's exactly what you have here, right? I mean, now you're like in particles with long range, well, kind of long range-ish interactions, longer than your range of your volume. If you take, and you have a pressure you don't realize, it's called social pressure, because if you get too many people in here, you will have to push them out of the room because of the COVID restrictions. So that's how it happens. So in practice, the same story is happening for your molecules here.
I have questions. Whether if in the case we calculate the CP and CV and then we compute the difference between them. For example, if the difference is R equal to R, so can we conclude that this system is not ideal gas?
If it is equal to R, you want to know whether, if it's equal to R...
So can I conclude that the system is ideal gas?
Strictly speaking, no. Because in order to get, so you see, if A is equal to 0, but B is not equal to 0, this term is not there. But still, this function is one of those functions for which dEdV is equal to 0, right? But I wouldn't call this an ideal gas, because it's a gas with hardcore interactions. So strictly speaking, there is some interaction. If you increase the volume beyond if you increase the density beyond a certain scale, you will start seeing this interaction, because you get, it's like billiard balls, right? If you put too many of them, practically they cannot move. So you will start seeing this interaction, but it is, well, probably the van der Waals approximation is not going to be appropriate at high densities. I wouldn't call, I mean, to my taste, I wouldn't call this an ideal gas. Okay? So it's a good question, your question, but I wouldn't call this an ideal gas if you have hardcore interactions. However, it is true that from the point of view of the van der Waals equation, you still, I mean, you're not seeing a major effect if you neglect the long-range interactions and have only hardcore interactions, right? Now, the reason is the following, that van der Waals equation of state is still a correction to the ideal gas equation of state that is valid at low densities. So you're still thinking about molecules that are very far apart with you know, billiard ball-like behavior. Now, if I look at the moon, if I look at stars on a scale that is that of the, you know, on my scale that is much smaller, of course they, you know, or on the scale of their distance, sorry. If I look at stars on the scale of their distance, they look like point particles, right? And that's why here you don't see anything. When you set the long-range interactions equal to 0, since they are very distant in this approximation, because you're low density, you don't see anything, any effect of these billiard balls. So all I'm saying is that at this level is just terminology, right? And saying, okay, I have short-range interactions, I don't want to call it an ideal gas, but for all purposes, it is an ideal gas. Now, you will see the difference when you start increasing the density, because if you have short-range interactions and you start increasing the density, you will start seeing that the constraint will not make them move as ideal particles. Okay?
So does it mean that van der Waals is valid when it is for long-range interaction?
No, van der Waals is valid when is actually the first correction to the ideal gas. So what do I mean by this? If you make an expansion, which is what we will do, why? Share content, screen. If you make an expansion and your small parameter is essentially the density, okay? So this is going to be the first correction in that expansion, essentially. Okay? So, let me put it this way. The ideal gas is the limit in which the density tends to 0. Right? It's very, very small. If the density is not 10 to the minus 6, but is, I don't know, 0.1, then you use this first correction, which is the van der Waals equation. But then if the density keeps growing and growing and growing, and your molecules get closer and closer and closer, the van der Waals equation is not valid anymore. It's another approximation. It's a correction to the... You see what I mean, right? It doesn't make sense to think about excluded volumes when your particles are as close as the size of your, as the excluded radius. Doesn't make sense to do this. You see? All right, so now last exercise of thermodynamics. What?
So, I don't know how you get from the CP to be that form.
Yes?
Yeah, I mean, like from that to that.
What do you want?
No, I just a little bit confused.
From here? From this?
No. You substitute dV dt with at constant pressure.
Yes.
Into that equation, right? And then
Yes.
you get CP. The second term, I don't.
Now this one? You're confused about this one? Oh look, man.
It's just the. Or is there any?
Just a second. dV dt. How do you get to this? Well, you have to substitute for P. So you have to. So look at. Don't ask me to do the algebra here, right? I mean, but what you have to do is you have to write P equal to RT over VB minus A, V minus B minus A over V squared, right? And you substitute it here. So you see that the V squared goes with the V squared, you get RT minus VB, which is fine. And now you get this dv dt blah blah blah, which is r divided by p minus blah 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 blah. Again, you substitute for p that story. So you get r times t divided by v minus p minus, plus or minus? Minus 2a over v squared plus 2ab divided by v cubed. Now, and now you do the algebra and you get what you should get, I hope.
I get it.
I hope you get it. I mean, check it. It makes it look. I didn't redo the calculation now. I mean, the only reason I suspect that is correct is that in the limit in which a is equal to 0, it gives me the result that I know for the ideal gas. And this is what I was talking about last time. You remember that I told you in the final exam you do a calculation. Suppose you have done this algebra and you get a final result and you have absolutely no idea whether your algebra is correct or not because you were nervous, you didn't eat enough, you drank too much coffee, too much wine the day before, etc., etc. And you have no idea. So how do you do it? You check limits, right? You remember, okay, the ideal gas is R. Okay, let's check what happens when A goes to 0. And the fact that A has to go to 0 and not B suggests that perhaps this formula is correct because, as you could see before, what was important was A equal to 0 and not B. For B, you get a dV equal to 0 as for the ideal gas. All right, so final question I wanted to ask with you, which is the following. Let's consider again the expansion of an ideal gas at adiabatic expansion, right? And from an initial volume to a final volume. And now I ask myself the following. How is the temperature going to change when I perform this expansion? Okay? Okay, so now the solution to this exercise uses some identities that I have to tell you, even though I hate them, which are the following, called the chain rules. They work as follows. If I have three variables, A, B, and C, then dA dB at constant C times dB dC at constant A times dC dA at constant B is equal to -1. This is the chain rule number. Well, chain rule. And in addition to this, dA dB at constant C is 1 over dB dA at constant C. Okay?
Why -1?
Why -1? Because look, these are things from mathematics, so let's read them on Wikipedia.
No, I mean, why not 1?
Why not 1?
Yeah, that's all.
Because they say so. I don't know. I don't remember the proof.
Okay.
I don't remember. Let's check that it's correct. -1. Chain rule, thermodynamics. Chain rule, thermodynamics. Yeah, it's a -1. I'm sorry, it's a -1. I don't know. Look. I don't remember the proof. But you can find it on Wikipedia. So, go to Wikipedia and find it. Alright, so this chain rule tells us that dt, dv, constant E, dv, de, the constant t, de, dt, the constant v is equal to -1. And therefore, dt, dv at constant E is equal to -1 over dv, de at constant t, de, dt at constant v. Alright? And this is equal to, now I use the second rule, dE, dV, minus dE, dV at constant t divided by dE, dt at constant v. But what is dE, dt at constant v? That is the heat capacity, right? So this is -1 over CV dE, dV at constant t. Okay? Agree?
Yeah.
Great. Fantastic.
Oh, wait. Just
No, I'm not going. We should sing it like opera. Constant V, constant V. Okay. Everybody's ready?
Or
What?
going to the next.
Going to the next. Yeah, but if you keep reading the telephone, you will miss the interesting part. Okay, so now dV dt at constant dV at constant t we already calculated 10 times, and this is equal to 1 over CV P minus T dP dV dt at constant V, right? According to what we calculated before 10 times, dV at constant t is equal to blah blah blah. Therefore, if I now substitute the van der Waals equation of state, what do I get? I get that this is equal to 1 over CV, right? Minus A over V squared. Right? And therefore, delta T is now equal to minus A over CV integral between V initial and V final dV of 1 over V squared. Right? So, which is equal to now minus A over number of moles squared divided by CV integral V initial V final dV over V squared. And this is equal to minus A n squared heat capacity, sorry, plus 1 over V final minus 1 over V initial. And you see again that what? Okay, so and you see again that if you have a non-ideal gas, in this expansion you also have associated a change in temperature, which is not there for the ideal gas, right? Because for the ideal gas, internal energy, well, in this process, the internal energy is not changing because it's adiabatic, right? So there is no exchange of heat with the external environment. There's no work done. So everything is closed. It's a free expansion. So internal energy is not changing, and therefore the constant should be, the temperature should be constant for the ideal gas. And now you see that if instead of having an ideal gas, you have a non-ideal gas, then the temperature is not constant, but is actually changing. How is it changing? Well, let's check the sign of this result. I think it's correct, because if V final is bigger than V initial, the temperature is decreasing. So as you expand the gas, the temperature is getting lower, which makes sense, right?
Yes.
Physically, this is what you expect. So we are happy, right?
Yes, we are.
We are happy. Great. So now that we are happy and we have seen a lot of thermodynamics and we have been extremely patient, now we can start with statistical mechanics. Yeah, it's like a stadium. Statistical mechanics. Here we go. Stat mech. Stat mech. We are ready for stat mech. So, all right. You can do statistical mechanics. So, as I told you many times, statistical mechanics is the way to start from microscopic stuff and make it become macroscopic. Okay? So start from the description of dynamics of molecules and make it become a description of the air in this room. Start from the description of patterns of this table and make it describe the table itself. And whatever, many different things. Now, when you think about statistical mechanics, you have to have in mind what are the degrees of freedom you are trying to describe. The microscopic degrees of freedom. Now, microscopic degrees of freedom could be the position and momenta of your particles, of your molecules, right? So, microscopic degrees of freedom. So the microscopic degrees of freedom could be what? Could be the positions and momenta of all molecules in this room, right? So for I equal to 1 to n, if you're describing a gas, for a gas. If you're describing a magnet, for example, the magnetization vector for each individual ion that is composing your magnet, right? Now, how this magnetization, well, this magnetization vector is actually not a classical variable, it's a quantum mechanical spin. But let's simplify our life to the extreme and think about spins as vectors in classical mechanics, okay, for the moment. So Therefore, my microscopic variables could be, for example, if I have what is known as a uniaxial magnet. Uniaxial means there is only one axis on which the system can be magnetized, right? So if I have a uniaxial magnet, my microscopic vectors could be Ising type variables, right? Which have value I equal to from plus and minus 1 for magnet. Now, if instead you have a system in which your magnetization vector can vary everywhere in space, on a sphere, let's say, then sigma I is a vector of, let's say, a unit vector, or something with a fixed magnitude that can rotate in space. And in that case, you have a Heisenberg type magnet, or a magnet with a SO3 symmetry, or whatever you call it the way you want. But you see, you're always trying to describe a system that has some microscopic degrees of freedom. That could be the motion of particles of a gas, the vectors of magnetization of a magnet, whatever, right? Statistical mechanics can be used also to describe, I don't know, how much money you have in the bank that is fluctuating, all this kind. You can have many variables. Now, in addition to this, it's not enough to specify what are your microscopic degrees of freedom. You have to specify what is the dynamics of your microscopic degrees of freedom, right? And typically you have Newton dynamics, right? So how do you specify the dynamics? You specify the dynamics writing up an Hamiltonian function, right? So an Hamiltonian function I know everybody is getting, this is an H, is a fancy H.
Actually, it's in H in Vietnamese.
Is a what?
Similar to H in Vietnamese.
In Vietnamese?
But
Really?
yes, it's combination of H and H, 2H.
Wow, fantastic. You see?
Yeah.
I'm able to do things that I didn't know I'm able to do.
In Vietnamese, we write something like that.
Fantastic. Okay, is an H in Vietnamese.
Actually, when you write N, it's also similar to N in Vietnamese.
Okay.
Okay.
Okay, so it's an H in Vietnamese. So it's a Hamiltonian. It could be, for example, pi sum over I, pi squared over 2m plus some interaction potential. In case you describe a gas. Now, in case you describe a magnet, your Hamiltonian is going to be a function of your sigma I. And for example, if I have a uniaxial magnet, the simplest possible model I can write down is the so-called Ising model, in which pairs of spins are interacting according to this interaction here. I'm sure that you've all seen the Ising model. Ising, not Ising, Ising, okay, Ising model. And, well, this is the Hamiltonian. Ising. Is Swiss. He was Swiss. He's that. Now.
We basically tortured his name.
Well, it's like my name Alessandro has many possible incarnations depending on the country you go to. Alessandro. Alexandro. Alessandro in Russian. Anyway, so, okay. So you understand the logic. Every time you try to solve or to model something in statistical mechanics, you have to think, first, what are my microscopic degrees of freedom? Second, what is my Hamiltonian? And then third, you have to make the connection between microscopic dynamics and macroscopic behavior. Now the connection comes through what is called the equal a priority postulate, probability postulate. So I'm going to write it here in Vietnamese. Equal a priori probability. Postulate. Okay, so this is the key postulate of statistical mechanics, the basic idea. Now, what is the basic idea? The basic idea is the following. Suppose that you have many systems. So, suppose that you have, let me describe it this way. Suppose that I have many copies of my system, which are all in the same macroscopic conditions, right? So there are tons of copies of the same system, all in the same macroscopic conditions. All right, what does it mean? For example, if I have a thermally isolated system, they have all the same internal energy. Same volume, same number of particles, same internal energy, right? So, and now I go in my phase space and draw the hypersurface of all microscopic states that correspond to these macroscopic conditions. In other words, if I have a gas, I take the hypersurface in phase space that has constant energy, number of particles, and volume, right? And that is going to draw for me the surface in this phase space. Very nice surface. And now I start playing the following game. Okay? The game is the following. For each of the copies, I measure the macroscopic state. The macroscopic state is the same from the beginning. Now, for each of the copies, I'm a super powerful experimentalist, and I measure the microscopic state. So the position and momentum of all particles. Let's say I'm able to do that. I'm not, but let's say I'm able to do that. Then, and then I do the following. I measure for this, and I put a point on this surface for the state that I measured. Okay? And then for that, I measure another state, I put another point. And then for this, I put another point. Okay? And I do so for tons of these copies of my systems. For a number of copies n that is much, much larger than one that actually tends to infinity. Super huge. Now, the equal a priori probability postulate tells me that if I play this game and do this exercise, these points will cover my surface uniformly. Okay? Uniformly, you know what is uniformly. When you paint or uniform covering means that you have the same density of points everywhere. Okay? So that is the idea. Now here I just explained to you practically what it means, this equal a priori probability postulate, using what is known as a frequency interpretation of probability theory. Now, the fancy way to say what I just said here, thinking like an experimentalist in mathematical terms, is the following. All microstates which are consistent with the observed macrostate, macro, have equal probability to occur. Or microstate, okay, I'll read it.
Has equal probability to
Probability to occur. Yeah, I didn't.
To occur.
No, to occur.
Sorry, I didn't hear that.
To occur. Okay, so this is the statement. All microstates corresponding to the same observed macrostate, micro, macro, have same probability to equal probability to occur. This is the mathematical translation of saying that the density of points in this hypersurface, if I perform this experiment, is going to be uniform. Okay?
Can I also say that there is no overlap between the points? Because you say that the density is uniform.
Well, I mean, you can measure twice the same point. It's not forbidden, but then all other points you will measure more or less twice. I mean, you know, the density is uniform means that it's not necessary that they are not the same. You can measure. I mean, it's not forbidden to measure twice the same configuration. But overall, density is going to be uniform. Okay? Now, all of this is actually a very intuitive way of thinking. I mean, it's just telling you, look, in this room, you can, instead of thinking in terms of many copies of the same system, you can also think about the same system observed at different times. If the conditions, the macroscopic conditions are not changing, the microscopic state of the system is changing continuously, actually. But it's always consistent with the same macroscopic conditions, volume, number of particles, and energy, right? You agree? And now, what is going to happen if you think this way? Well, what is going to happen is that in this very nice hypersurface, you have this little microstate which will start evolving in time and do whatever, blah, blah, blah. And then what is going to happen is that this line, this time evolution of this guy, is going to color uniformly. It's like when you were kids. I don't know, I mean, from when I was a kid, the teacher in daycare were asking me to color uniformly the paper with the pencil. Okay, so it's going to do the same. Color uniformly without overlaps the hypersurface. So this is called an ergodic system in the mathematical terminology. All right, so good. So now let's see how we formulate this in mathematical terms. Well, we say the following: the probability density of observing the microstate Q and P is as follows. if you have, okay, here we encounter the problem, the following problem. If you are dealing with the phase space of a gas, so if I fix the energy, and I fix just the energy, I define an hypersurface. Now, an hypersurface, a surface in a volume has measure 0, like a line. You see what I mean? So, in order to make it something that I can measure, I have to make out of a surface a lasagna. You know what is a lasagna? You know what it is, right? You know what is a lasagna. Guys, let's talk about important stuff. You know what is a lasagna. You don't know what is a lasagna? You know?
I don't know.
You don't know? No. You don't know what is a lasagna?
Yeah.
Unbelievable. Okay, I'll bring you the recipe. You can buy your stuff and make it yourself. This is crucially important. So it's a type of pasta. It's a, no, I mean, you cannot go away from this country without eating lasagna. Please. Since now you cannot go to restaurants, you have to make it yourself. Anyway, so how do you make out of a surface a lasagna? You make it thick, right? So to make it thick, you say the following. I have that this probability is constant when the energy, the Hamiltonian, which is the energy function, is between a certain energy and an energy plus delta, where delta is a thickness that is arbitrary but is much smaller than E. Okay? So this in practice amounts to taking this guy and making it a bit thick, like this, in a sense.
Why again you want to make it thick?
Because when I want to get something that has a finite volume. You will understand later on why. They want to get something that has a finite volume. So it's constant in this thing and is equal to 0 otherwise. Now, you could think experimentally as your delta as the resolution of your instruments that are measuring the energy. So when I say I have a certain macro state, so I'm saying I have a certain energy, number of particles and volumes, these are 3 macroscopic variables that I'm measuring with some apparatus and with a certain resolution. So you can think of delta as the resolution of your experiment. Okay? And what I'm saying is that within the resolution of your experiment, which is super good, much smaller, delta is much smaller than E, all microstates in this hyper lasagna, not hypersurface, are equally probable. Okay? And all the others are not even observed because they are not consistent with the macroscopic conditions. All right, so next time you are going to see the consequence of this postulate. And we are going to derive the entire statistical mechanics just from this postulate and from another observation, which is the Boltzmann identity for the entropy, which is going to follow from this. Okay?
Discuss that.
Okay, so now I can show you, I can turn off. Oh no, I cannot turn off. Okay, I move